Good day, ladies and gentlemen, boys and girls, and friends and neighbors. Today we're going to talk about these logistic growth models and their derivatives. This is going to be a very important topic in BC calculus. It's a fairly, at first glance, it seems like a difficult topic, but really it is not that difficult. If you look at this function here, it looks kind of confusing. It really isn't. So let's start talking about it. The first thing I want to do, since it's been so long since I've seen all of you, and this picture is not going to come out very well, but I'm going to give it a whirl anyway. And here I am. So I want to say hi to all of you, and you know that's not what I really look like. And this is the first time I've taken a video of myself with Smart Notebook. The picture probably will not be clear, but that's okay. I just wanted to say hi. And back to logistic differential equations, or logistic growth models. So the first thing we're going to do, this particular model, this particular function, this P of t yields the total population of something. So this is your P of t. The output is P of t of this particular model. And this is the graph. This particular graph is given here. That's this graph of P of t. This is the graph of P of t. This guy right here is our t values. And we're going to go t is some moment of time. And we don't know what the units of time are. We don't know what the units of the population are. But right now, this is the model right here. This is what we're looking at, is this graph. And all I want to do at this point right here is look at some characteristics of this graph, where P of t is the output, time is the input. Well, if I look at this, it appears that the population is going to reach a maximum amount. So let's write that down here. If I see as t goes to infinity, as t approaches infinity, if time goes on, what's happening to the population? The population is approaching some number. The population is approaching some number, and we can easily figure out what that population is, what that population does approach, if I look at this graph right here. So if t approaches infinity, this right here, we know this, as t approaches infinity, this guy right here, e to the negative 0.3t, that guy approaches 0. And you can look at the graph, and this is another point about these videos. At any time that you want to check the math, check the math. You can put e to the negative 0.3x in your graph. As x goes to infinity, you're going to see that that goes to 0. So this is a decreasing exponential. But this exponential is embedded in this logistic growth model. So as t goes to infinity, we can do a series of steps here. As t goes to infinity, this particular guy goes to 0. So 15 times that goes to 0. And this is what I have, 15.393 times that goes to 0. So my population is actually going to 1,000 over 1 plus 0, which is 1,000. So what does that tell me? That tells me then that this guy right here, I can draw a horizontal line right here, and I will. And that horizontal line, I need to grab the line. See, yeah, that horizontal line, that's going to be 1,000. So as t approaches infinity, the population approaches 1,000. No mystery here. The other thing, if I'm looking at this graph, you might pause the video and wrap your head around this statement right here, if you will. The other thing, if I look at this graph is growing at the beginning of the population. When t is equal to 0, I see down here at t equals 0, right after t is equal to 0, that population is growing. It's increasing pretty darn quick. And then there's some time, some moment, some time here that the population begins still increasing, but it's increasing slower, i.e. the graph goes from concave up to concave down at some point. So there is an inflection point, and we recall what an inflection point is. So I'm going to just sketch a vertical line. I'm going to sketch that bad boy in yellow. Make sure that it's parallel with the y-axis there. I'm going to grab a hold of that line, hopefully. And I'm going to note that there is a point in that graph where the graph changes from concave up to concave down. That means that this population, the rate that this population is growing, because the population is growing quite quickly here. It's growing quite quickly, and then it starts to slow down. It has to slow down because that's what's the difference, the biggest difference between a logistic growth model and an exponential growth model. Exponential growth models continue to grow exponentially, and that's not realistic. So the more realistic growth model is this thing we call the logistic growth model, and that's what we have. So we're increasing at this inflection point. The rate begins to get slower. Okay, the rate decreases. The graph is still increasing, but the rate is going to be decreasing. We're going to talk about that at the next slide. Let's see, is there anything else interesting about this? Well, I could maybe talk about this point 0, p of 0. There is a initial population, if you will. Oh, and what would that initial population be? I could look at that. I could easily find that. P of 0 is certainly going to be, what is it going to be? It's going to be 1,000 over 1 plus 15.393. Because again, if t is equal to 0, this guy right here, 0.3 times 0 is 0, e to the 0 is 1, so that's the initial population right there. And I think this comes out to 16 something. So, all right, so let's see here. Is there anything else? I don't think so. So I have on the next slide this result just to make sure that I talked about everything. Okay. Oh. Point the rate begins to slow. The inflection point. I talked about this. Here's what was not on that other slide was this guy right here. And we're going to be able to prove this. What's really interesting about these logistic growth models is that right at the inflection point, right where the rate begins to slow down, that equals half of the maximum carrying capacity. So for our model, this line right here, the output of this input at that inflection point, that's going to be, we don't know, I mean, we can figure out what that t is, and we will later on, the time that it takes for the population to reach half of its maximum capacity. But we will figure that out later. But there is a time that yields half of the maximum capacity. And we think about the calculus, which we're about to go into a little bit, we'll be able to figure out that. That's going to happen. That t sub 1 is going to happen where the derivative of this guy right here is going to be 0, because the derivative is going to go from increasing to decreasing. Without further ado, let's see, is there anything else? Okay, we know this. I talked about this. You might take some notes on that. That's just, I had this on the previous page. So what I'd like to do at this point is I'd like to look at this guy right here. This, and this is given without proof, this is the derivative of this population. So this is the derivative given that p of t is equal to the function 1,000 over 1 plus 15.393 e to the negative 0.3t. And you could go, if you want to, you could go and find the derivative of that. But this, I'm going to just talk about the derivative, and this is given without proof. But this is my population model, and this is the guy that we want to talk about, this differential equation. And note that this differential equation is in terms of p. This is not in terms, this derivative, this dp dt, if you will, is not in terms of t as the population is. This dBdt is in terms of p, the population. We need to note that. So this is a logistic, what we call a logistic differential equation. And I will tell you, differential equation. We will not need to be able to solve that differential equation and show that it's equal to that. All we need to do is be able to analyze this differential equation, okay, in terms, and we're going to analyze it in terms of this population P. And what do we know? So I have the differential equation in factored form, and it's kind of easy to see that the derivative, true or false, is equal to 0. When is the derivative is equal to 0? Well, when p is equal to 0, that's what makes this portion 0. If p is equal to 0, that factor, there's two factors here, 0.003p, and then the other factor is 1,000 minus p. Those are the factors of that differential equation. This guy is 0 when p is 0. When is this guy 0? This guy is 0 when p is equal to 1,000. And that makes sense from our previous model that the derivative is going to 0 when the population reaches 1,000. If I go back to this curve here for a moment, and that's exactly what happens. As t goes to infinity here, the derivative is going to go to 0. The derivative is the slope of the tangent line. So as t goes to 0, t goes to infinity, sorry, the population, or pardon me, the derivative of the population, this guy right here, dB dt, that rascal goes to 0. And it is 0 when p is equal to 0 as well. Let's go back to our analysis of the analysis of the derivative. What else do we know about that? Well, what else can we tell about that? Let's see here. Well, oh, okay, let's do this for giggles. Let's multiply this dPdt out. So what I'm going to do is multiply that through, and now I'm going to get 0.003, well, times 1,000 times, well, let's see here. Sorry. P times 1,000. Multiplying this term by this, I'm just doing simple distributive property, minus 0.0003 p times p, which is p squared. So that's the derivative multiplied out. And so what is 1,000 times 0.0003 is that's going to be 0.3p minus 0.0003 p squared. And guess what we're going to do? What we're going to do, because what I said earlier in a previous video was that, oh, this is the point, this inflection point is the point that the rate of change, i.e. dP dt, increases and then it starts to decrease. So, hey, this derivative better have a maximum point. Let's see where we are. Better have a maximum point somewhere. And it does indeed. This is a quadratic. And if I look at the coefficient of this is a quadratic, the leading coefficient is negative. So that daggone graph, the graph of dB dt, is indeed going to have a maximum point just by the nature of the algebra behind this equation. So how are we going to find where that derivative, it's increasing, then decreasing? How do we find that? We're going to find the derivative of the derivative. So what we're going to do here is we're going to take the derivative with respect to t of this guy right here, And what is that? This is a really easy derivative to find. This portion here is a constant times p. It's just 0.3 minus 2, bring the 2 down, times 0.0003 p. Bam. And now I want that thing to be 0. Where is that thing 0 at? Because I want to find out where this thing has a maximum. So I'm going to find out where the derivative, i.e. the second derivative right here, dt squared. I want to find out where that's 0 at. Well, that guy is going to be 0 when this portion is equal to that. So that's going to happen when 0.3 is equal to 2 times 0.0003p. And if I solve that for p, I have 0.3 divided by 2 times 0.0003. And that, given without, you can stop the video, check the math, when the population is 500. So all I did here was prove what I was telling you on this slide here, was that this graph does indeed, the inflection point does indeed happen when the population is 1/2 of the maximum capacity. That's all I've done. So dB dt is a maximum. The derivative is a maximum at half of the carrying capacity. That's important to note. So let's see here. Is there anything else that I want to say about this analyzing this derivative? Let's see here. I have analyzed it on the next slide, and let's see here. This is my p of t. Okay, got all that. Found the second derivative. It does indeed. I think that's all I want to say about this. If I go to the next slide, you should be able to tell me what the next slide is. Oh, the next slide, on the same slide, it gives me the population, and it also gives me the derivative of the population with respect to t. So this is the derivative, and this is the population. And you notice, oh, the derivative does indeed. No one's going to ask you to create this graph, but it's nice to know this thing does indeed. Let's see, what color am I in? Pretty perfect color. This thing does have a maximum, and guess what happens at that maximum? That maximum, guess what? Well, we already know that. Pull that guy out. Whoa, you're grabbing the wrong thing, big dog. And let's go in green just to keep everything constant here. No pun intended. So right there at that intersection, that's going to be, this point right here is 1,000. And this output is 500. And this is right here where the derivative is a maximum. Okay, because the second derivative is 0 there. Alrighty, so you might need to pause and think about what's going on here. Okay, same thing I have here. We looked at the connection of the two graphs. So let's make a general consensus here. Here's the general, in general. And so I got some constants here. Now this is the differential equation here. This is the differential equation. K is the constant growth. M is the carrying capacity. Just like the model we just looked at. You might have to look at that. K is the growth constant. We call that the growth constant, which in our case, what was that growth constant? It was 0.0003. That was what our K in our example was. The maximum capacity in our example was 1,000. And if I'm given this differential equation, I can automatically solve it. But keep in mind, nobody's going to ask you to go from here to here. Nobody's actually going to ask you to go from here to here. All they're going to do is they're going to ask you to analyze this derivative. So they're going to ask you to analyze this differential equation. When is the population a maximum? When is the derivative 0? Things of that nature. A note here, in our example, m times k was equal to 0.3. And then the negative, it was negative 0.3. And you can do this you can show that P of t, the second derivative, is 0 when P of t is 1/2 m. So if I take this, if I find the second derivative, here's the first derivative. I'm going to do this simple little mathematics here, multiply through by kp, and I have k mp minus kp squared. And I find the derivative of that. I want to find the second derivative. I want to differentiate that with respect to t, as I'm going to do right now. This is a simple polynomial in p. This is going to be km. This is going to be minus 2kp. And that guy is equal to 0. This second derivative is equal to 0, again, just like I did before, when km is equal to 2kp. When does that happen? When the population is 1/2 of the carrying capacity. So we're going to end this video, and my suggestion here to you would be to watch this video a couple times. I will assign some, I believe this will be a BC topic on this year's test. They're only going to have a few free response questions, probably 2, maybe 2.5, maybe 2 larger ones. But I think in light of our current situation with the coronavirus, and I'm going to post a video about the curve, flattening the curve later on, but there is a lot of similarities between that what we want the coronavirus curve to look like and a logistic growth model. So I believe that this particular year they're going to have a logistic growth model. So what will be my suggestion? To watch this video a couple times. And I'm going to end by going back here, and Tigger is signing out. See you soon.